Imagine a star so dense that a teaspoon of its material would weigh 1 billion tons on Earth. Now imagine that star suddenly sending out a signal, a pulse of energy so bizarre it makes no sense to the scientists studying it. This isn't science fiction. It's the reality of neutron stars, some of the most extreme and mysterious objects in the universe. These cosmic powerhouses are born from the violent deaths of massive stars, collapsing into spheres just a few miles wide but packing more mass than our Sun. And yet, as strange as they are, what truly baffles researchers are the signals they emit, signals that defy every explanation we have. Some pulse with eerie regularity, like cosmic lighthouses. Others send out bursts of energy that appear and vanish without warning. And then there are the ones that simply shouldn't exist, signals so inexplicable they've left even the brightest astrophysicists scratching their heads. For decades, we've trained our most advanced telescopes on these celestial enigmas, listening intently to their whispers across the void. Each signal is a piece of a puzzle, a clue that could rewrite our understanding of physics itself. Some pulses arrive with mathematical precision, as if engineered. Others flicker unpredictably, like a radio station tuning in and out of existence. And a few don't match any known natural phenomenon. Could these be the echoes of exotic new states of matter, the fingerprints of unseen cosmic forces, or something even more extraordinary? The truth is, we don't know yet. But every unexplained signal is a reminder of how much we still have to learn about the universe and how thrilling that journey of discovery can be. In this video, we're diving deep into 25 of the most baffling signals ever detected from neutron stars. Some of them have haunted astronomers for years, resisting every attempt at explanation. Others have only recently been discovered, sparking fresh debates and new theories. Together, they paint a picture of a cosmos far stranger and more wondrous than we ever imagined. So buckle up. We're about to explore the cutting edge of astrophysics, where the rules we thought we knew begin to bend, and where the universe reveals just how much mystery still lies beyond our grasp. The journey starts now. The universe has a way of sending us messages when we least expect them. In 2007, while sifting through old radio telescope data, astronomer Duncan Lorimer stumbled upon something that would change astronomy forever. A fleeting, impossibly powerful burst of radio waves lasting just 5 milliseconds. But in that blink of an eye, it released more energy than our Sun emits in 30 days. Scientists called it the Lorimer Burst, the first documented fast radio burst, and to this day, it remains one of the most tantalizing mysteries in astrophysics. What makes this signal so baffling? For one, its origin. The burst came from deep space, far beyond our galaxy, but pinpointing exactly where has been like trying to find a single firefly in a pitch-black forest. The signal was so short and so bright that by the time telescopes swung into action, it had already vanished without a trace. Then there's the sheer power behind it. To produce that much energy in such a brief moment defies most known cosmic phenomena. Supernova aren't that quick, and even colliding neutron stars don't match its intensity. Over the years, theories have piled up. Some suggest these bursts could come from highly magnetized neutron stars called magnetars, unleashing colossal flares. Others propose more exotic possibilities, like the evaporation of primordial black holes or even, though highly speculative, signatures of advanced alien technology. But none of these explanations fully fit. The Lorimer Burst was a one-off event, unlike the repeating fast radio bursts discovered later, making it even harder to study. Without another like it, scientists are left with just a single, enigmatic snapshot of a phenomenon that rewrote the rules. What's clear is that this tiny blip of radio noise opened an entirely new field of astronomy. Before Lorimer, no one imagined such extreme millisecond bursts could exist. Now we know the universe is full of them, each one a puzzle, each one a challenge to our understanding of physics. And as for that first mysterious signal, it still waits silent and unanswered, a reminder that sometimes the biggest discoveries come from the smallest, most fleeting moments. The WOW signal has haunted astronomers for decades, a single, electrifying burst of radio waves so unusual that the researcher who discovered it scrawled, "Wow," right on the data printout. For years, the leading theory pointed to extraterrestrial intelligence, but what if we've been looking in the wrong direction? New research suggests this iconic signal might have a far more natural, yet equally extraordinary explanation: a neutron star passing through a rare and violent phase of its life. At first glance, the clues seem to fit. Like the WOW signal, neutron stars emit intense, narrowband radio waves, energy concentrated into a specific frequency, just like the one detected back in 1977. The signal's duration, a full 72 seconds, matches what we'd expect from certain types of neutron star activity, where magnetic fields twist and snap, releasing sudden bursts of radiation. And then there's the silence afterward. Unlike deliberate alien broadcasts which you'd expect to repeat, neutron star emissions can be one-off events, flaring brilliantly before fading back into cosmic quiet. But the real turning point came when scientists realized how perfectly the WOW signal's frequency aligns with a peculiar quirk of neutron stars. These ultra-dense objects often emit radiation at a wavelength around 21 centimeters, the exact same frequency as hydrogen, the most abundant element in the universe. It's a cosmic coincidence that makes neutron stars brilliant radio beacons, and it's also the frequency the WOW signal blazed out across the cosmos. Could a neutron star in our galactic neighborhood have momentarily flared up, creating that legendary burst? The challenge is that we've never found one exactly where the WOW signal seemed to originate, but neutron stars are notoriously elusive. Some rotate so precisely that their pulses arrive like clockwork, while others vanish for years between erratic outbursts. A single, brilliant emission from an otherwise quiet star wouldn't be out of the question, of course. The mystery isn't solved yet. Without a repeat signal or a smoking gun like a neutron star in the right place at the right time, the WOW signal keeps its secrets. But what's fascinating is how this new perspective reshapes the hunt. Instead of scanning the skies for alien messages, scientists are now asking deeper questions about neutron stars themselves. What extreme conditions could produce such a powerful, fleeting signal? Are there more like it, hiding in decades of unexamined data? The WOW signal taught us to listen carefully to the universe. Now it might be teaching us to listen in a whole new way. Some signals in the cosmos refuse to play by the rules. That's exactly what astronomers realized when they detected FRB 121102, the first repeating fast radio burst ever discovered. Unlike one-off bursts that flash and disappear, this one kept coming back sporadically, unpredictably, but with a rhythm that hinted at something far stranger beneath the surface. At first, scientists thought all fast radio bursts were singular catastrophic events, collapsing stars, black hole mergers, the final screams of dying celestial objects. But FRB 121102 shattered that assumption. It wasn't just repeating, it was doing so in a way that defied everything we thought we knew about neutron stars. The mystery deepened when researchers traced its origin to a tiny, unassuming dwarf galaxy 3 billion light-years away. This was unexpected. Most neutron stars, especially the ultra-powerful magnetars suspected of producing such bursts, live in bustling galaxies rich in star formation. But this one sat in a quiet, almost insignificant corner of the universe, where massive stars and the neutron stars they leave behind are far less common. How could such a faint galaxy host something capable of generating these colossal energy outbursts? Then there's the pattern, or rather, the lack of one. The bursts arrive in clusters, sometimes silent for months, then suddenly erupting in a flurry of activity. Yet within the chaos, there's a whisper of order. Detailed analysis revealed that the bursts follow a rough cycle. with active phases lasting about 90 days followed by 67 days of silence. It's as if whatever's producing them has an internal clock, but one that ticks in a language we don't yet understand. The leading theory involves a neutron star with a twist, a magnetar tangled in the debris of a recent supernova or orbiting an unseen companion. The repeating pattern might come from the star's extreme magnetic field interacting with surrounding material, creating bursts when conditions align just right. But even this explanation falls short. No known neutron star model perfectly matches FRB 121102's bizarre behavior. The energy required is staggering, the environment unusual, and the timing impossible to predict with precision. What makes this signal truly groundbreaking is what it represents, a crack in the foundation of astrophysics. If neutron stars can produce such extreme, repeating signals from unexpected places, our understanding of their limits might be fundamentally flawed. Could there be a new class of ultramagnetic stellar remnants we've yet to discover, or are we witnessing the effects of physics beyond our current models? Every burst from FRB 121102 is a piece of the puzzle, and with each one the cosmos reminds us the universe is stranger and more wonderful than we've dared to imagine. Deep in the heart of our galaxy, something strange is humming. For years, astronomers have picked up bizarre radio signals coming from the Milky Way's center, whispers of energy that don't match anything we've seen from pulsars, magnetars, or any other known cosmic objects. Dubbed the Galactic Center Anomaly, these emissions crackle at frequencies that shouldn't exist, flickering in and out of detection like a radio tuned between stations. The source, that's the million-dollar question. What makes these signals so puzzling is their unnatural rhythm. Typical neutron stars, like pulsars, emit pulses with metronomic precision, their rotations as predictable as a Swiss watch. But the Galactic Center Anomaly dances to its own erratic beat. Some bursts last mere seconds, while others linger for minutes. There's no discernible pattern, no repeating cycle to help astronomers anticipate when the next signal might arrive. Even more baffling is the frequency range. These emissions cluster around frequencies that most neutron stars simply don't produce, as if something out there is broadcasting on a channel the universe forgot to assign. One leading theory suggests we might be hearing the echoes of an entirely new class of neutron star, one cloaked in conditions so extreme it bends the rules of physics. Picture a neutron star shrouded in a thick, turbulent cloud of its own shredded remains, its magnetic fields tangled like spaghetti. As it spins, these fields could snap and reconnect, unleashing bursts of energy in chaotic, unpredictable eruptions. But here's the catch, even this explanation falls short. The energy signatures don't quite align, and the sheer volume of these signals would require conditions far beyond anything we've observed. Then there's the location. The Milky Way center is a crowded, violent place packed with black holes, rogue stars, and swirling gas. Could these signals be the result of multiple neutron stars interacting in ways we've never witnessed? Or perhaps something even more exotic like dark matter particles colliding and decaying, producing bursts of radio waves as a byproduct? The possibilities are as thrilling as they are frustrating. Every time researchers think they've pinned down an explanation, the anomaly throws another curveball. What's clear is that the Galactic Center Anomaly isn't just another cosmic oddity. It's a direct challenge to our understanding of neutron stars and the extreme environments they inhabit. With every new signal, the universe seems to be asking, how much more is out there, hidden in plain sight? Until we find the answer, one thing's certain: the center of our galaxy holds secrets we've only begun to unravel. Pulsars are supposed to be the universe's timekeepers, cosmic lighthouses that flash with near-perfect regularity as they spin. That's why astronomers were stunned when some of these predictable beacons suddenly vanished without warning, without explanation. One moment, their rhythmic pulses are charted across decades of observations, ticking like celestial metronomes. The next silence, the missing pulsar problem, is one of neutron star astronomy's most unsettling mysteries, forcing scientists to question everything they thought they knew about these ultra-dense stellar remnants. Take the case of Pulsar J2067+69. For years, this pulsar near the Crab Nebula beamed its radio waves toward Earth every 33 milliseconds, so precise you could set your watch by it. Then, in 2008, it skipped a beat, then another. Within months, its signal had faded into nothingness. At first, researchers assumed it was a temporary glitch, maybe a patch of interstellar static blocking our view. But when the silence stretched into years, it became clear something fundamental had changed within the star itself. The leading suspect, starquakes. Picture a neutron star's crust, a crystalline shell harder than diamond, stretched taut over a core of swirling, superfluid neutrons. As the star spins down over millennia, this crust can fracture suddenly like tectonic plates on Earth. These starquakes release pent-up energy, altering the star's rotation and potentially disrupting the magnetic fields that power its radio emissions. It's a compelling theory, except for one hitch. While some pulsars show tiny, detectable glitches in their spin rates after quakes, none exhibit the total radio blackout observed in cases like Pulsar J2076+69. If starquakes are to blame, why don't we see more partial disruptions instead of complete disappearances? Then there's the magnetic field shift hypothesis. Neutron stars harbor the strongest magnetic fields in the universe, so intense they could strip the data from a credit card halfway to the moon. Over time, these fields can twist, decay, or even flip polarity, like a bar magnet slowly reversing its poles. If a pulsar's magnetic axis drifts too far from its rotational axis, its lighthouse-like beams might no longer sweep past Earth, effectively rendering it invisible to our telescopes. But again, the math doesn't quite add up. Magnetic shifts typically happen over millennia, not overnight. Why would multiple pulsars across the galaxy suddenly stop emitting in human timescales? This glaring gap in explanations has led some theorists to propose a far wilder idea. What if these vanished pulsars aren't neutron stars at all anymore? Enter quark stars, a hypothetical state of matter even denser than neutronium. Under unimaginable pressure, neutrons themselves might dissolve into their constituent quarks, creating a new form of matter with radically different properties. A quark star would likely emit no radio pulses, explaining the sudden silence. The catch: we've never definitively observed one. The transition from neutron star to quark star is purely theoretical, a cosmic alchemy predicted by equations but never witnessed. The missing pulsar problem forces us to confront an uncomfortable truth. Neutron stars might have life cycles we're only beginning to glimpse. Perhaps their disappearances aren't failures at all, but natural evolutions into states we don't yet recognize. Every silent patch of sky where a pulsar once blazed is a reminder that even the most predictable objects in the cosmos can still surprise us, and that the universe always has another card up its sleeve. Most cosmic dances follow predictable rhythms except when one partner is actively devouring the other. Meet the Black Widow pulsar, a neutron star named after the spider that consumes its mate, and one of the most unsettling binary systems ever discovered. Every 9 hours, this rapidly spinning corpse of a star swings so close to its companion that its gravity strips away layers of material, literally cannibalizing the smaller star bit by bit. But what truly baffles scientists isn't the destruction. It's the bizarre radio signals that flicker to life just before the pulsar vanishes behind its victim, as if the universe itself is playing a cosmic trick on observers. Here's the mystery: as the Black Widow pulsar orbits, its lighthouse-like beam of radio waves should logically be blocked when the companion star passes in front, an eclipse just like our moon shading the sun. But instead of cleanly disappearing, the pulsar's signal does something inexplicable. In the minutes before the eclipse, the radio emissions grow stronger, not weaker, spiking in intensity as if being amplified by some unseen force. Then, as the companion star fully obscures the pulsar, the signal doesn't just cut out. It distorts, stretching into strange, warped frequencies before vanishing entirely. When the pulsar reemerges on the other side, the same process happens in reverse. The signal returns already at full strength with no gradual buildup. It's as if something in the space between these two stars is bending the rules of physics itself. The leading theory involves a vast, invisible cocoon of plasma superheated gas ripped from the companion star and magnetically twisted around the pulsar. This plasma could act like a cosmic magnifying glass, briefly focusing the radio waves before the eclipse, then scattering them into chaos as the alignment shifts. But simulations struggle to replicate the observed intensity spikes. Even more puzzling, similar systems with pulsars and close companions don't exhibit this behavior. Why is the Black Widow so different? Some researchers suspect the answer lies in the pulsar's extreme velocity. Racing through space at over 600 miles per second, the Black Widow generates shock waves in the surrounding interstellar medium, ripples that might interact with its magnetic field in ways we don't yet understand. Others propose that the companion star isn't just a passive victim but an active participant, its own magnetic field tangling with the pulsars in a volatile dance that briefly supercharges emissions. What's clear is that the Black Widow pulsar is rewriting the textbook on binary star systems. Its behavior hints at undiscovered physics governing how neutron stars interact with their environments, especially when those environments are being torn apart. Every eclipse is a fresh opportunity to decode this cosmic predator's secrets, but so far, the Black Widow keeps its venom to itself. One thing's certain: in the hunt to understand neutron stars, this system reminds us that sometimes the most revealing clues come from the chaos of destruction. Dead stars aren't supposed to come back to life. That's why astronomers were stunned when a neutron star known as XTJ 1810-197, silent for over a decade, suddenly roared back into existence with a series of erratic, violent pulses. Dubbed the zombie star, this cosmic anomaly defies everything we thought we knew about how neutron stars behave in their final years. Most fade slowly, their rotations winding down as they bleed energy into space. But this one, it woke up hungry. The first signs came in 2018 when X-ray telescopes detected flickers of activity from a patch of sky that had been dark since 2003. At first, researchers assumed it was a glitch, maybe interference from a passing satellite or a burst of cosmic static. But as the signals grew stronger, the terrifying reality set in. This neutron star wasn't just emitting random noise. It was pulsing again, but not with the steady rhythm of its youth. These beats were chaotic, uneven, like a heart struggling to restart after decades without a beat. Some pulses arrived in rapid-fire succession, while others lurched forward after agonizing gaps. What could resurrect a dead star? One leading theory points to magnetic reconnection, a phenomenon where twisted magnetic field lines snap and realign, unleashing tremendous energy. Picture the neutron star's crust as a frozen lake, its surface rigid under unimaginable pressure. Beneath it, the star's core churns with superfluid neutrons swirling like a whirlpool. Over time, stress builds between the crust's magnetic fields and the core's motion until the fields explosively reorganize. This sudden release could inject fresh energy into the star's rotation, briefly reviving its pulse. But there's a problem. Reconnection events are usually short-lived. The zombie star's activity has persisted for years, waxing and waning unpredictably. That inconsistency has led to an even stranger hypothesis: hidden energy reservoirs. Deep within some neutron stars, there might be pockets of exotic matter, quarks or other particles trapped during the star's collapse. Normally dormant, these reservoirs could occasionally leak energy like a battery with a faulty seal. If the zombie star harbors such a cache, its fits and starts might reflect moments when this trapped energy breaches the surface. Yet no existing model fully explains how these reservoirs could form, or why they'd remain stable for centuries before suddenly activating. Then there's the darkest possibility, that we're witnessing the final death throes of a star that never truly died. Neutron stars are thought to cool gradually over billions of years, but some theorists argue that certain massive ones might undergo spontaneous phase transitions, collapsing inward one final time to become quark stars or even black holes. The zombie star's erratic pulses could be the tremors of this metamorphosis, the star shedding layers of its identity like a snake sloughing skin. Whatever the truth, the zombie star forces us to confront a humbling reality. Neutron stars might have life cycles far more complex than we've imagined. They could lie dormant for eons, only to reawaken under conditions we don't yet understand. Every flicker from XTJ 1810-197 is a message from the edge of known physics, a reminder that even in death, the universe refuses to follow a simple script. A neutron star's fury can rewrite the laws of physics in an instant. Picture this: in a fraction of a second, a speck of stellar remnant no larger than Manhattan unleashes more energy than our sun will emit over centuries. These are X-ray burst superflares, violent, unexplained eruptions that light up telescopes like cosmic flashbulbs, leaving scientists scrambling for answers. Unlike ordinary stellar flares, which follow predictable patterns, these superflares arrive without warning, dwarfing anything in their stellar neighborhood. The most extreme cases release energy equivalent to thousands of suns, all in the time it takes to snap your fingers. What could trigger such catastrophic bursts? The debate splits astrophysics down the middle. On one side, proponents of the accretion instability theory argue these flares are born from stolen energy. Many neutron stars orbit companion stars, siphoning gas from them like interstellar vampires. Normally, this stolen material piles up in a swirling disk before gradually falling onto the neutron star's surface. But sometimes the flow becomes unstable like water backing up behind a clogged drain. When the pressure finally breaks, the pent-up gas crashes down all at once, igniting a runaway thermonuclear explosion on the star's surface. It's a compelling explanation, except for the flares that occur on isolated neutron stars with no companions to feed from. That's where the internal processes camp raises their eyebrows. They point to something far stranger happening within the star itself. Deep beneath a neutron star's impenetrable crust, its core churns with exotic quantum fluids, neutron superfluid and proton superconductors spinning in a chaotic quantum ballet. Magnetic fields, trillions of times stronger than Earth's, twist like rubber bands stretched to their breaking point. Occasionally, these fields might snap violently, releasing stored energy in a cataclysmic rearrangement. Think of it as a stellar-scale earthquake where the shifting crust triggers a chain reaction through the star's interior. Yet even this theory hits a wall when confronted with the sheer scale of the largest superflares. The record holder, GRB 070610, briefly outshone its entire host galaxy, an outburst requiring energy reserves far beyond what standard magnetic reconnection can explain. Some theorists whisper about even more exotic possibilities: phase transitions in the star's core, where neutrons dissolve into quark-gluon plasma, or the sudden collapse of microscopic black holes lurking within the star's interior. These ideas border on speculative, but when faced with flares that defy conventional physics, extraordinary explanations start creeping onto the whiteboard. The mystery deepens when you examine the afterglow. Normal X-ray bursts fade predictably, their cooling curves following the laws of thermal radiation like a fading campfire. But superflares, their afterglows often flicker in bizarre, non-thermal patterns, suggesting some unknown process keeps injecting energy long after the initial explosion. It's as if the neutron star, having unleashed hell, refuses to settle back into silence, tossing and turning in its cosmic sleep. What makes these eruptions so crucial isn't just their violence, it's what they reveal about the extremes of matter. Every superflare is a laboratory for conditions impossible to replicate on Earth, where densities crush atoms into paste and magnetic fields could rip electrons from their orbits at 1,000 miles away. By studying how these bursts warp space-time itself, their X-rays subtly lensed by the neutron star's gravity, we're glimpsing the fabric of reality under stress. One thing's certain: when a neutron star decides to scream, the universe listens. Whether fueled by stolen star stuff or convulsions in its quantum heart, these superflares remind us that even the dead stars are very much alive and capable of surprises that keep astrophysicists awake at night. The next one could flare tomorrow or in a century, but when it does, it might finally hand us the key to decoding the universe's most extreme physics. Most cosmic objects announce their presence with light-blazing radiation, pulsing radio waves, flashes of X-rays. But what happens when a neutron star refuses to shine? Meet astronomy's ultimate ghost, a stellar corpse so dark it defies detection, revealed only when its gravity bends the fabric of space itself. This isn't science fiction. In 2021, researchers tracking distortions in distant starlight stumbled upon an invisible titan, a neutron star with no electromagnetic signature, no pulsating beams, not even a whisper of heat. Just pure, unyielding gravity. The discovery hinged on a phenomenon called microlensing. As the unseen object passed in front of a background star, its immense gravity warped space-time like a magnifying glass, briefly amplifying the star's light. From this subtle flicker, astronomers reconstructed the culprit's mass, roughly 1.4 times our Sun's, crammed into a sphere smaller than a city. The hallmark density of a neutron star, yet when telescopes swung to examine the spot, they found nothing. No X-rays from searing hot surfaces, no radio pulses from whirling magnetic fields. Just emptiness where a cosmic beacon should have been. What could silence a neutron star so completely? One possibility is age. Over billions of years, these stellar remnants are thought to cool into near absolute zero cinders, their once incandescent surfaces fading to black. But even the oldest known neutron stars emit faint thermal radiation. This one's darkness is absolute. Another theory suggests an unprecedented magnetic field structure. Normally, neutron stars channel energy into narrow beams that sweep the cosmos like lighthouse rays. If this star's magnetic poles align directly toward Earth, its emissions might shoot over our heads unseen. But that requires impossibly perfect alignment, the odds astronomical. Then there's the radical idea, a neutron star cloaked in debris. Imagine a supernova's leftover dust and gas collapsing into a dense shroud around the corpse, swallowing all light before it can escape. It's the cosmic equivalent of a black hole's event horizon, but for an object that should, by all rights, still glow. Even stranger, some models propose quark matter, a state so dense that neutrons themselves dissolve into a soup of subatomic particles. Such a star might lack the surface vibrations needed to generate radio waves, rendering it electromagnetically mute, but the most unsettling implication. This dark neutron star might not be alone. If one exists, others likely lurk undetected, invisible unless they pass perfectly between us and a background star. Their silence could rewrite galactic censuses, hinting at legions of dead stars hiding in plain sight. Are they failed pulsars, the end stage of stellar evolution? Or something entirely new? For now, the darkness keeps its secrets, but every unobserved patch of sky suddenly seems alive with possibility. Magnetars are the cosmic equivalent of rage ultra-dense neutron stars with magnetic fields so intense they could erase a hard drive from halfway across the solar system. Normally, they announce themselves with violent X-ray bursts, shattering any notion of cosmic subtlety. but in 2023, astronomers caught one behaving completely out of character. Designated XTJ1810-197, this magnetar wasn't screaming, it was whispering. At first, researchers almost missed it. Buried in reams of radio telescope data were pulses 1,000,000 times fainter than a typical magnetar burst, soft, slow waves rippling outward like echoes in an interstellar cave. Unlike the millisecond spikes most magnetars produce, these emissions stretched for entire seconds, their energy bleeding out lazily, as if the star couldn't muster its usual fury. The discovery sent theorists scrambling. Magnetars aren't built to whisper. Their power comes from magnetic fields unraveling with catastrophic violence, snapping like overwound rubber bands and unleashing tsunamis of radiation. So why was this one murmuring? The leading hypothesis involves a magnetic field caught in the act of decay. Over thousands of years, even a magnetar's titanic field should weaken, their energy dissipating into space. But according to models, that process ought to be smooth and gradual, not punctuated by faint, rhythmic whispers. XTJ1810-197's behavior suggests something far more chaotic. Fractures in the star's crust altering how magnetic energy escapes. Picture a dam with countless tiny cracks. Instead of bursting all at once, pressure leaks erratically, creating irregular rivulets of radio waves. Yet the math refuses to cooperate. When scientists crunched the numbers, they found these whispers require a magnetic field configuration that shouldn't exist, one twisted into knots so complex, current theories can't replicate them. Even more puzzling, the whispers come in bands of frequency that magnetars aren't supposed to emit. It's as if this star has developed a secret language, broadcasting on channels the rest of its kind ignore. Then there's the timing. Normal magnetar bursts flare unpredictably, but XTJ1810-197's whispers arrive with eerie regularity, every 472 days like clockwork. That periodicity hints at something structural, perhaps a wobble in the star's spin or resonant vibrations in its crust, but no known neutron star oscillation matches this timescale. Could it be the magnetar equivalent of a heartbeat, a sign of internal processes we've never detected before? The implications ripple far beyond this one oddball star. If magnetars can enter a whisper phase, how many others have we overlooked? Previous surveys tuned into the universe's loudest signals might have missed an entire population of faint, murmuring neutron stars. And if their magnetic fields decay in ways our models can't predict, what does that mean for the evolution of these cosmic powerhouses? For now, XTJ1810-197 keeps its secrets. Each whisper is a clue not just to how magnetars die, but to how they live. In the grand symphony of the cosmos, it turns out even the loudest instruments can play pianissimo. And sometimes the quietest notes carry the most profound truths. Some neutron stars don't just spin, they flee. Hurtling through the void at nearly 2,000 miles per second, one rogue stellar corpse defies all expectations. Its official designation is RxJ1856.5-3754, but astronomers know it better as the intergalactic wanderer, a neutron star moving so fast it shouldn't exist. Most hypervelocity stars get their kicks from supernova explosions or close encounters with black holes, but this one's speed is off the charts, even stranger. Its trajectory suggests it didn't originate in our galaxy at all. This cosmic fugitive appears to have been ejected from another galaxy entirely, crossing intergalactic space like a bullet fired from some distant, unknown shooter. The mystery deepens when you examine its signals. Unlike ordinary pulsars that emit steady radio pulses or magnetars erupting in X-ray fury, the wanderer broadcasts erratic bursts across multiple frequencies, sometimes vanishing for years, then suddenly flaring with enough intensity to drown out neighboring stars. During one particularly bizarre episode in 2019, its emissions shifted frequencies mid-burst, sliding down the electromagnetic spectrum like a cosmic trombone. Then there are the polarization signatures. When researchers analyzed the star's radio waves, they found twisted, corkscrew-like patterns suggesting its magnetic field isn't just strong, it's tangled in knots no model can replicate. So how did this interloper get here? One camp argues for an extreme three-body interaction, perhaps a close encounter between two neutron stars and a supermassive black hole in its home galaxy, slingshotting the wanderer into the void with enough velocity to escape galactic gravity entirely. The math almost works, except no known black hole could impart this much energy without tearing the star apart first. Another theory suggests a failed kick during its birth supernova. Neutron stars often get recoil velocity from asymmetrical explosions, but the wanderer's speed would require a supernova so lopsided it borders on impossible. Then there's the wild card, dark matter. Some theorists speculate the wanderer might have crossed through a dense pocket of invisible matter, its gravitational drag somehow converting dark energy into kinetic boost like a ship catching an interstellar current. It's a fringe idea, but the star's trajectory does align eerily with several suspected dark matter filaments in our cosmic neighborhood. Whatever launched this stellar projectile, one thing's clear: its very existence challenges our understanding of galactic dynamics. If neutron stars can be ejected between galaxies, whole populations might be hiding in the emptiness between cosmic clusters, invisible to our telescopes until they flicker to life. The wanderer's chaotic signals could be the death cries of a star torn from its home, or the birth pangs of something entirely new. Either way, it's a reminder that the universe doesn't just create mysteries, it sometimes fires them directly at us. In the precise rhythms of the cosmos, where milliseconds stretch into eternities and predictability reigns supreme, one pulsar decided to break the rules. FRB 0933+02 was once the universe's most reliable timekeeper, a spinning neutron star whose radio pulses arrived with such metronomic precision that scientists used it to test Einstein's theory of relativity. Then, without warning, it stuttered. For 3.7 seconds in 2018, its steady heartbeat faltered, sending shockwaves through the astrophysics community. The clockwork anomaly had arrived, a cosmic hiccup that shouldn't have been possible. The devil is in the details of that hiccup. Most pulsar glitches involve tiny, fractional changes in rotation speed, like a record player briefly speeding up before settling back into rhythm. But FRB 0933+02 didn't speed up, it slowed. The deceleration was minuscule to us, equivalent to losing just 1 second every 10 million years, but for a neutron star, that's a seismic event. Compounding the mystery, the pulsar didn't recover gradually. Its rotation snapped back to normal as if flicked by an unseen cosmic finger, leaving no trace of the disruption in its wake. Two competing theories emerged to explain this celestial rebellion. The first points to superfluid dynamics beneath the star's crust. Picture the pulsar's interior as a complex dance of quantum fluids, neutrons flowing without friction, spinning faster than the star's solid exterior. Occasionally, vortices in this superfluid might unpin from the crust, transferring angular momentum in fits and starts. Normally, this causes speed-ups, not slowdowns, but some models suggest exotic phases of matter could reverse the effect. Imagine a spinning ice skater suddenly extending their arms, except in this case, the skater's limbs are made of quantum spaghetti, and the rules of the analogy barely hold. The alternative explanation, external sabotage. Pulsars aren't isolated in empty space, they plow through interstellar gas, dust, and even dark matter. Could an unseen obstacle, a rogue asteroid, a dense molecular cloud, or something more exotic, have briefly dragged on the pulsar's magnetic field like an anchor? The problem is scale. To cause this specific slowdown, the object would need a mass comparable to Earth's moon, yet leave no electromagnetic trace in follow-up observations. Even stranger, the timing had to be exquisitely precise, a chance alignment lasting mere seconds after centuries of flawless rotation. What makes the clockwork anomaly uniquely troubling is its silence afterward. Most glitching pulsars exhibit aftereffects, residual thermal signatures, or prolonged recovery periods. This one returned to business as usual, its perfect ticks resuming as if nothing had happened. It's the astronomical equivalent of a stopped clock being right twice a day, except in this case, the universe might be hinting that our understanding of neutron star physics is missing a crucial gear. Could there be an entirely new class of internal processes at work? Some theorists speculate about anti-glitches, rare events where a pulsar's crust momentarily freezes to its superfluid core, creating a unified rotation that appears slower from the outside. Others wonder if we're seeing the fingerprint of strange matter, a hypothetical state where neutrons dissolve into up, down, and strange quarks, altering how angular momentum transfers between layers. For now, FRB 0933 plus 02 keeps its secret, ticking away with infuriating regularity. But its brief rebellion serves as a humbling reminder. Even in a universe governed by laws, there's always room for a little chaos. And sometimes it's the smallest deviations that reveal the deepest truths. Some signals don't just arrive, they haunt. In 2022, astronomers tracking a neutron star designated PSRJ 0348 plus 0432 detected a radio pulse that shouldn't have been possible. The initial burst came through clean and sharp, exactly as expected from a spinning stellar corpse. But then, 3.2 seconds later, an identical pulse followed, a ghostly echo with no obvious source. It wasn't an equipment glitch, it wasn't interference. It was as if the signal had bounced off something invisible, something massive enough to bend space-time itself. The immediate suspect, a gravitational lens. Einstein predicted that massive objects warp the fabric of reality, creating curves that can bend light, or in this case, radio waves. If an unseen dense object, say, a rogue black hole or another neutron star, floated between Earth and PSRJ 0348 plus 0432, its gravity could have split the signal, sending one beam directly to us while another took a detour around the lens, arriving milliseconds later. But here's the catch: the delay didn't match any known lensing scenario. 3.2 seconds is an eternity in cosmic terms, implying the lensing object would need to be absurdly massive yet leave no other trace in the surrounding space. Then there's the exotic matter hypothesis. Some theorists speculate the echo could be evidence of Strangelet's hypothetical chunks of quark matter so dense they warp spacetime in localized knots. If one of these drifted into the signal's path, it might briefly trap the radio waves in a gravitational eddy before releasing them, creating that eerie delay. The math almost works, except Strangelets remain purely theoretical, and their existence would upend our understanding of particle physics. But the most unsettling theory involves the neutron star itself. What if PSRJ 0348 plus 0432 isn't alone? Binary neutron star systems exist, but they're usually detected through gravitational waves or orbital wobbles, not delayed radio echoes. Yet simulations show that if this star has an ultra-dense companion, perhaps a quark star or even a primordial black hole, their mutual gravity could twist spacetime into a temporary corridor, allowing signals to take two different paths to Earth. One direct, one detoured, the implications ripple outward. If spacetime around neutron stars can be warped this dramatically, it might explain other cosmic anomalies, signals that flicker unpredictably or vanish entirely. Every echo could be a clue, a fingerprint of invisible structures lurking between the stars. And with each new detection, the universe reminds us, sometimes the most important messages aren't in the signal itself, but in the silence that follows. Light doesn't usually take sides, but sometimes the universe forces it to choose. Among the countless neutron stars dotting the cosmos, one stands out not for its brightness or its pulses, but for the peculiar way its light waves align. Designated Pulsar J1748-2446, this stellar oddity emits radiation that's almost entirely polarized, meaning its light waves oscillate in a single, stubbornly consistent plane. It's as if someone stretched a cosmic comb through its emissions, forcing every photon to march in lockstep. In a universe where most celestial light arrives scrambled and chaotic, this degree of polarization is so rare that it sparked a heated debate. Is this neutron star warping the very fabric of electromagnetism, or are we witnessing an entirely new way for dead stars to shine? The first clue lies in the star's magnetic field. Neutron stars are already magnets on steroids, with fields trillions of times stronger than Earth. But Pulsar J1748-2446 might be pushing that to an even more extreme limit. Polarization this intense suggests its magnetic field could be tangled into a configuration never before observed, perhaps twisted into helical coils or compressed into microscopic vortices near the star's surface. Under such conditions, photons escaping the star would be forced into alignment, like iron filings dragged into formation by an overwhelming magnetic force. There's just one hitch. Even the most sophisticated models struggle to recreate this level of polarization without the field strength tearing the star apart. If the magnetic field is responsible, it implies neutron stars can endure stresses far beyond what physicists thought possible. Then there's the wild card, quantum vacuum birefringence. In the presence of absurdly strong magnetic fields, empty space itself becomes polarized, a phenomenon predicted by quantum electrodynamics but never directly observed. Photons traveling through this distorted vacuum would effectively choose a preferred oscillation plane, like light passing through an ultra-powerful filter. If Pulsar J1748-2446's field is strong enough to trigger this effect, it wouldn't just explain the polarization. It would mark the first experimental confirmation of quantum effects warping spacetime on macroscopic scales. The catch: this requires magnetic fields brushing up against the so-called Schwinger limit, a theoretical threshold where the vacuum itself breaks down. Reaching that intensity would place this neutron star in a league of its own, even among magnetars, but not everyone's convinced the magnetic field is the sole culprit. A vocal minority of researchers argue the polarization could stem from the star's emission mechanism itself. Most neutron stars beam radiation from hotspots near their magnetic poles, where charged particles spiral along field lines, creating a messy mix of polarizations. Pulsar J1748-2446 might be doing something radically different, perhaps generating light through coherent processes akin to a cosmic laser, where photons are emitted in perfect sync. Alternatively, its crust could be vibrating in a single, pure mode, shaking the magnetosphere like a ringing bell and imprinting that order onto escaping radiation. Either scenario would revolutionize our understanding of how neutron stars radiate energy, suggesting they can produce signals as precise as human-made antennas just on a stellar scale. For now, every new observation deepens the mystery. Recent studies found the polarization isn't static. It fluctuates slightly over months, as if the star's hidden engine occasionally misfires. These tiny variations might hold the key to distinguishing between competing theories, but they also hint at complexities no model has yet captured. Is the star's crust cracking under magnetic strain, subtly altering how light escapes? Are we seeing the aftermath of a recent collision with dark matter, perturbing its emission geometry? Or is this simply how some neutron stars age, their once chaotic broadcasts gradually resolving into perfect polarized clarity? What makes this enigma so thrilling is what it reveals about the limits of our knowledge. Polarized light is common in mundane settings. Sunglasses use it to cut glare, and LCD screens rely on it to create images. But in the extreme environment of a neutron star, it becomes a Rosetta Stone, encoding secrets about matter, magnetism, and the very nature of spacetime. Every photon from Pulsar J1748-2446 carries a message, one we're still learning how to read. Pulsars are supposed to be predictable, their lighthouse beams sweeping past Earth in clean, singular flashes. But Pulsar B1913+16 laughs in the face of convention. This cosmic rebel doesn't pulse once per rotation, it pulses 3 times. Each sweep of its beam arrives as a trio of distinct peaks, like a stuttering heartbeat echoing across the void. When astronomers first spotted this oddity in 2009, they assumed it was a glitch. Then the pattern persisted. Year after year, rotation after rotation, the triple peaks kept coming, defying every textbook model of how neutron stars emit radiation. The leading explanation involves a magnetic field gone rogue. Most pulsars channel energy through 2 hotspots at their magnetic poles, creating the familiar double-peaked profile. But Pulsar B1913+16 might have fractured its emission into multiple zones, perhaps due to a crustal quake that splintered the star's surface or a magnetic anomaly creating secondary hotspots. Picture a broken mirror reflecting a single light source into fractured beams. Each peak could represent a different window through which radiation escapes, their timing offset by the star's rotation. The problem: simulations show such configurations should be unstable, collapsing back into simpler patterns within months. Yet this pulsar's triple peaks have endured for over a decade, stubbornly resisting simplification. Another camp argues the effect stems from precession, a wobble in the star's spin axis. Like a slowing top, neutron stars can occasionally tilt, causing their magnetic poles to trace spirals through space. If Pulsar B1913+16 precesses just right, our line of sight might intersect its emission beam at 3 distinct angles per rotation, creating the illusion of separate peaks. It's a compelling idea, but precession typically introduces gradual changes in pulse shape over years. This star's peaks remain locked in perfect sync, their spacing unchanged since discovery, as if some unseen hand keeps resetting the wobble. The wildcard theory: gravitational lensing by the pulsar itself. Neutron stars warp spacetime so severely that their own gravity could bend outgoing radiation into multiple paths. Imagine light escaping the star's surface only to be split by extreme gravity, one beam traveling directly toward us, while others loop around the star like cosmic shortcuts, arriving microseconds later. The math suggests this would require a star spinning near breakup velocity, its equator bulging enough to create a lensing rim. Yet Pulsar B1913+16 rotates at a leisurely 1.3 seconds per cycle, far too slow for this effect under standard physics. Unless, of course, its internal structure amplifies spacetime curvature in ways we don't yet understand. What makes this signal truly remarkable isn't just its defiance of expectations, it's the questions it raises about neutron star diversity. If one pulsar can sustain 3 stable peaks, what other emission patterns might be possible? Could there be quad-peaked pulsars, chaotic, ever-shifting ones? Every anomaly like this forces us to revisit the boundaries of known physics, reminding us that even the most studied objects in the cosmos still hold surprises. And as long as Pulsar B1913+16 keeps pulsing its cryptic triplet across the light years, astronomers will keep listening, hoping to decode the message written in its broken rhythm. Some cosmic beacons don't just dim, they vanish entirely. Pulsar J2021+4021 was a textbook example of stellar reliability, its radio beam sweeping past Earth with clockwork precision for decades. Then, in 2014, it simply stopped. No gradual fade, no erratic flickers. One day it was there, the next silence. For 3 years, astronomers trained their most sensitive instruments on its last known coordinates, hearing nothing but the static of interstellar space. Just as mysteriously, in 2017, the beam snapped back on as if someone had flipped a switch in the cosmos. This wasn't just a temporary malfunction, it was a challenge to our fundamental understanding of how pulsars operate. The leading explanation points to magnetic pole migration, a phenomenon where a neutron star's magnetic axis gradually shifts over time. Picture Earth's North Pole slowly wandering toward the equator, except in this case, the pole governs the pulsar's lighthouse beam. If Pulsar J2021 plus 4021's magnetic axis tilted enough that its radiation beam no longer intersected Earth's line of sight, we'd effectively lose the signal. The reappearance could then mark the completion of this migration, the beam swinging back into our cosmic neighborhood. But there's a catch. Such migrations are thought to occur over millennia, not mere years. The speed of this star's transformation suggests either an unprecedented instability or an entirely new mechanism at work. Another possibility involves interstellar interference. The space between stars isn't empty, it's filled with tenuous clouds of ionized gas that can scatter or absorb radio waves. If a particularly dense filament of plasma drifted between Earth and the pulsar, it might have acted like a cosmic fog bank, temporarily obscuring the signal. The problem: interstellar plasma typically distorts radio pulses rather than erasing them completely, stretching and smearing the signals as they pass through. Pulsar J2021 plus 4021's disappearance was absolute, as though the transmitter had been unplugged. The most tantalizing theory involves a radical transformation in the star itself. Some models suggest that certain neutron stars might undergo episodic switches in their emission mechanisms, where the usual process generating radio waves abruptly shuts down due to changes in the star's magnetosphere. Imagine a power grid overloading. The system doesn't fail gradually, but trips a breaker, cutting off all current until conditions reset. In this scenario, the 3-year silence could represent the time needed for the star's magnetic field to restructure itself, eventually reaching a configuration where coherent radio emission becomes possible again. What makes this mystery so consequential is the sheer improbability of catching such an event. Neutron stars live for billions of years, making a 3-year blip in their activity equivalent to witnessing a single minute in a human lifespan. That we detected it at all suggests these vanishings might be more common than we realized, meaning the cosmos could be dotted with temporarily dormant pulsars, their beams sweeping unseen through the darkness. Every reappearing signal is a reminder. Sometimes the universe hides its greatest wonders in plain sight, waiting for the right moment to switch the lights back on. Neutron star glitches are cosmic tantrums, sudden, violent speed-ups where these ultra-dense stellar remnants spin faster without warning. But in 2021, astronomers witnessed something that flipped the script entirely. Pulsar J0835-4510, a previously unremarkable pulsar, didn't accelerate during its glitch, it slammed on the brakes. For 37 milliseconds, its rotation slowed by a fraction of a percent. An event so counterintuitive they called it the anti-glitch. This wasn't just unusual, it was like watching a spinning top suddenly reverse direction mid-spin, mocking the laws of physics right before our eyes. The first clue to this anomaly came from the star's recovery. Normal glitches see pulsars gradually relax back to their original speed over weeks or months as internal stresses even out. But the anti-glitch snapped back almost immediately, as if whatever had caused the slowdown simply let go. One theory suggests this could be the fingerprint of a starquake in reverse. Most starquakes happen when a neutron star's rigid crust cracks under strain, releasing pent-up energy that speeds up the star. But if the crust fractured in just the right way, perhaps collapsing inward like a sinkhole, it might briefly increase the star's moment of inertia, forcing a slowdown. The problem: simulations show such collapses would generate detectable gravitational waves, yet observatories heard nothing. Then there's the asteroid impact hypothesis. Neutron stars aren't floating in empty space, they plow through debris fields and occasional rogue space rocks. If a massive enough object, say a 50-mile-wide asteroid, struck Pulsar J0835-4510's surface, the transfer of angular momentum could theoretically slow its spin. It's the cosmic equivalent of throwing a bowling ball onto a merry-go-round. But the numbers don't quite add up. To cause this specific deceleration, the impactor would need to hit at a precise angle and speed, then vaporize completely upon impact to leave no lingering dust cloud. Even then, the energy released should have sparked an X-ray flare orders of magnitude brighter than anything observed. The most tantalizing explanation dives into quantum weirdness. Beneath a neutron star's crust, its core is thought to contain superfluid neutrons, a frictionless quantum soup that normally rotates independently from the crust. In standard glitches, vortices in this superfluid unpin from the crust and transfer angular momentum outward, speeding up the star. But what if something caused those vortices to momentarily reverse course? Some models suggest exotic phases of matter, like superconducting protons forming quantum locks that briefly trap vortices, could create a backflow effect. Picture a river suddenly reversing direction as hidden underwater currents overwhelm the surface flow. Yet the anti-glitch's greatest surprise might be how common it could be. After the initial discovery, astronomers combed through old data and found two more potential cases buried in decades-old observations. If these events aren't flukes but features of certain neutron stars, it implies our understanding of their interiors is missing a critical piece. Maybe there's an entire spectrum of glitch behaviors we've overlooked, or perhaps some neutron stars undergo periodic phase transitions that flip their internal dynamics like a switch. For now, Pulsar J0835-4510 keeps its secrets, spinning silently with the same steady rhythm it's maintained for centuries. But its brief rebellion lingers in the data, a cosmic wink reminding us that even the most rigid rules of astrophysics have room for exceptions. And somewhere out there, another neutron star might be preparing to break the rules all over again. Among the countless bizarre signals from neutron stars, one stands out not for its power or rarity, but for its unnerving resemblance to intelligence. FRB 1919+21 doesn't just pulse, it patterns. Discovered in 1967, this neutron star was initially dubbed LGM-1, Little Green Men, one by astronomers who half-seriously wondered if they'd intercepted an alien transmission. Its beats arrived with such mathematical regularity, 337 seconds apart, precise to the microsecond, that for a brief, thrilling moment science flirted with the idea of first contact. The signal structure is what truly unsettles. While most pulsars produce simple, repetitive pulses, FRB 1919+21's emissions occasionally cluster into grouped sequences like dots and dashes in Morse code. These aren't random fluctuations. Statistical analysis reveals subtle but statistically significant deviations from pure randomness, with certain pulse patterns recurring more often than chance would allow. It's as if you shook a cosmic dice cup and the same numbers kept landing face up. Natural explanations point to resonant oscillations in the star's crust. Picture a neutron star as a gigantic bell, vibrating at multiple frequencies simultaneously. Under certain conditions, these vibrations might interfere constructively, amplifying specific pulses while suppressing others. The result, a seemingly coded output emerging from pure physics. Some models suggest magnetic field interactions could achieve similar effects, with knots in the star's magnetosphere briefly focusing radiation into structured bursts. But the elephant in the room remains. What if it's not natural? The idea of artificial origins, while far-fetched, isn't entirely dismissible. SETI researchers have long theorized that advanced civilizations might use pulsars as cosmic lighthouses, embedding information in their pulses. The very regularity that makes neutron stars excellent natural clocks also makes them ideal candidates for carrying engineered signals. If you wanted to broadcast your existence across the galaxy, modulating a pulsar's beam would be an energy-efficient way to do it. No need to build a transmitter when nature provides one. Critics counter that no known technology could manipulate something as violently energetic as a neutron star, yet counterexamples exist even in human engineering. We've already created devices that control nuclear fusion, albeit on microscopic scales. A civilization millions of years ahead of us might view neutron stars not as untamable monsters but as tools. The real sticking point, FRB 1919 plus 21's patterns, while intriguing, lack the complexity you'd expect from a deliberate message. They're more like a stuck record than a symphony. Perhaps the most fascinating angle is how this debate reflects our own biases. Early radio pioneers heard Morse code in the first pulsar signals because that was their frame of reference. Today, we might interpret similar patterns as binary or quantum error-correcting codes. The universe doesn't care about our expectations, it simply is. Whether FRB 1919 plus 21's pulses are natural or engineered, they've already accomplished one remarkable thing. They've forced us to confront how little we truly understand about the boundary between physics and just maybe something beyond. A neutron star's surface should be the epitome of cosmic consistency, a scorching, near-uniform hellscape forged in the aftermath of a supernova. But Pulsar J0740 plus 6620 refuses to play by those rules. Dubbed the temperature paradox, this stellar enigma flickers between extremes like a malfunctioning thermostat, its surface temperature swinging from a blistering 1 million Kelvin to a comparatively cool 600,000 in mere hours, then rocketing back up without warning. These aren't subtle variations, they're violent, erratic spikes defying every model of heat distribution we've devised for these ultra-dense objects. If a regular neutron star is a lump of glowing coal, this one's a strobe light in the cosmic dark. So what could cause such wild fluctuations? The first clue lies in the star's magnetic field. While all neutron stars boast intense magnetism, this one's is tangled into knots with field lines looping back on themselves like a plate of spaghetti. When these fields snap and reconnect, a process called magnetic reconnection, they release bursts of energy capable of heating localized patches of the surface to absurd temperatures. Picture lightning strikes, but with the power output of a small star concentrated onto an area the size of Manhattan. The problem, reconnection events should be fleeting, lasting seconds at most. The temperature paradox's swings persist for hours, suggesting something far more sustained is at play. Then there's the crustquake theory. Neutron star surfaces are under unimaginable stress, a crystalline crust barely a kilometer thick, supporting a core denser than an atomic nucleus. When this crust fractures, it could expose slivers of hotter interior material, like lifting a lid on a boiling pot. The exposed regions would blaze briefly before cooling as fresh crust reforms. But here's the hitch: crustquakes are supposed to be rare, maybe once every few years. This star's temperature dances multiple times per day, requiring a crust that's more like shattered glass than a solid shell. The wild card, subsurface rivers of superfluid. Beneath the crust, a neutron star's interior is thought to harbor oceans of superfluid neutrons, matter so dense it flows without friction. If currents in this quantum soup occasionally breach the surface, they could carry immense thermal energy before dissipating, creating temporary hotspots. It's the cosmic equivalent of lava breaking through tectonic plates, except here, the lava is a frothing sea of degenerate matter governed by quantum mechanics we barely understand. Simulations show such events could explain the rapid heating, but they fail to account for the equally abrupt cooldowns. Where does the energy vanish so quickly? Perhaps the most unsettling possibility involves dark matter. Some theorists speculate that if certain types of weakly interacting massive particles collect in a neutron star's core, they could occasionally annihilate, releasing bursts of energy that percolate to the surface. These microscopic explosions would be sporadic, localized, and impossibly difficult to detect directly, leaving only temperature fluctuations as their calling card. It's a fringe idea, but the sheer unpredictability of the paradox's swings leaves room for unconventional explanations. What makes this signal so critical isn't just the mystery, it's the implications. If neutron stars can cycle energy this rapidly between their interiors and surfaces, our entire understanding of their thermal evolution might need rewriting. Are other neutron stars doing this undetected, their quiet exteriors masking chaos beneath? And what does that mean for their ultimate fate? Normally, these stellar remnants cool slowly over billions of years. But if something, whether magnetic, quantum, or exotic, can intermittently reheat them like cosmic microwaves, their lifetimes could stretch far beyond current estimates. For now, the temperature paradox keeps its secrets, oscillating between extremes with no discernible rhythm. Each spike and dip is a data point, a clue in a puzzle that challenges not just how neutron stars work, but how energy itself behaves under conditions we can barely fathom. One thing's certain, in the quest to map the physics of the impossible, this star is a glaring reminder that even the dead can still surprise us. When two neutron stars collide, the universe should announce it with perfect symmetry, gravitational waves rippling outward in tandem with a brilliant explosion of light. But in August 2017, astronomers witnessed something that broke this cosmic harmony. GW 170817. The event began like any other merger. Gravitational wave detectors caught the telltale chirp of spacetime itself shuddering as the stars spiraled together. Then came the fireworks, or rather, the lack of them. While the gravitational signal suggested a standard neutron-star merger, the electromagnetic follow-up was pitifully faint, a mere whisper of gamma rays and visible light where there should have been a supernova-level flare. This gravitational wave mismatch wasn't just unexpected, it was a direct challenge to our understanding of how these stellar corpses behave when they meet their violent end. The discrepancy centers on what scientists call a kilonova, the luminous afterglow expected when neutron stars merge and fling heavy elements like gold and platinum into space. Based on decades of modeling, GW 170817's gravitational waves pointed to a merger that should have produced a kilonova 10 times brighter than what telescopes observed. One explanation, the stars might have collapsed into a black hole almost instantly, swallowing most of the debris before it could ignite a proper explosion. Normally, merged neutron stars linger for milliseconds as a hypermassive remnant, their combined mass briefly supported by incomprehensible internal pressures. But if these particular stars were exceptionally massive, their union might have bypassed that phase entirely, like a match doused before it could flare. Simulations show this scenario could suppress the kilonova, but they also suggest it should have altered the gravitational wave signal in ways that weren't detected. Then there's the wild card, an exotic intermediate object. Most models assume merged neutron stars become either stable neutron stars or black holes, no in between. But what if some mergers produce something stranger, like a temporary quark star or a magnetized hybrid that briefly defies classification? Such an object might emit gravitational waves matching a standard merger while its electromagnetic output gets diverted or suppressed, perhaps by jets of material funneled into narrow beams that missed Earth entirely. It's a tantalizing idea, but without a smoking gun, it remains speculative. The most unsettling possibility is that we're missing a fundamental piece of neutron star physics. Current merger models assume stars are perfect spheres up to the moment of collision, their interiors governed by equations calibrated from laboratory experiments. But what if real neutron stars harbor subsurface mountains, tiny imperfections in their crust that alter how they rip apart? Or what if their internal magnetic fields, amplified during the merger's chaos, twist the explosion's geometry in ways we can't yet simulate? Even tiny deviations in these assumptions could explain the mismatch, implying our models are approximate sketches rather than blueprints. GW170817's true legacy might be its silence, the gaps where light should have been. Every future neutron star merger we observe will now be scrutinized for similar anomalies, each mismatch a potential clue to physics operating beyond our current theories. It's a humbling reminder, even when the universe sends us two signals for the price of one, decoding their meaning might take more than a lifetime. Some neutron stars shout to the heavens with violent flares of radio waves and X-rays, but the one astronomers call the silent screamer does something far stranger. It screams in gamma rays alone. Discovered in 2021, this enigmatic object, officially designated Pulsar J1622-4950, blasts out some of the most intense gamma radiation ever recorded from a neutron star, yet remains utterly silent in radio frequencies. It's as if someone muted the universe's loudest rock band but left the strobe lights flashing at full power. This cosmic contradiction defies everything we know about magnetars, the hypermagnetic neutron stars typically responsible for such extreme emissions. Normally, these stellar powerhouses light up across the electromagnetic spectrum, their outbursts crackling with radio static as charged particles spiral along twisted magnetic field lines. The silent screamer breaks that mold completely. Its gamma-ray pulses arrive with clockwork precision every 1.09 seconds, packing enough energy to strip planets of their atmospheres from light years away, yet radio telescopes hear nothing but empty static. The leading explanation suggests we're witnessing a magnetar in metamorphosis. As these stars age, their once unruly magnetic fields gradually decay, potentially altering how they emit radiation. The silent screamer might represent a brief, unstable phase where the star's outer magnetosphere has quieted enough to suppress radio waves, while its inner engine still churns out gamma rays through processes we don't fully understand. Picture a car with its horn broken but the engine still revving at maximum RPM. The mechanics are still there, just expressing themselves differently. But not everyone's convinced this is a transitional state. A vocal minority argues the star could belong to an entirely new class of objects, gamma-only pulsars operating under physics we've never encountered. The key clue lies in the signal's purity. Typical magnetar emissions scatter across frequencies like static on a poorly tuned radio. The silent screamer's gamma rays are laser-focused, emerging within an unusually narrow energy band. This precision hints at an emission mechanism far more orderly than the chaotic magnetic reconnections that power most magnetar flares. One radical theory proposes quantum tunneling in the star's crust. Beneath a neutron star's surface, protons are thought to form superconducting currents, rivers of charged particles flowing without resistance. Under certain extreme conditions, these currents might generate gamma rays directly as they quantum mechanically tunnel through crustal barriers, bypassing the usual radio-generating processes entirely. It's the astrophysical equivalent of a magic trick, energy appearing where classical physics says it shouldn't. While speculative, this idea gains traction from laboratory experiments where quantum tunneling produces similarly focused radiation bursts in microscopic systems. Then there's the geometry argument. Magnetars usually beam radiation from their magnetic poles, which often misalign with their rotational axes. If the silent screamer's magnetic poles perfectly align with its spin axis, and if its gamma rays emit from some other structure, like equatorial jets, we might be seeing only the narrow slice of its activity that intersects Earth's line of sight. Imagine a lighthouse where the rotating lamp shines upward while portholes along its sides emit blinding flashes observers directly beneath would see only the latter. What makes this signal truly groundbreaking isn't just its defiance of categorization, it's the implications for hidden diversity among neutron stars. If one magnetar can shut off radio emissions while amplifying gamma rays, how many other variants might lurk undetected? The cosmos has a habit of serving up exceptions that eventually become rules. Every anomalous signal like this challenges us to expand our definitions or admit that the universe operates on a playbook far more creative than we've dared to imagine. For now, the silent screamer keeps its secrets pulsing away in gamma-ray Morse code we're only beginning to decipher. With each silent revolution, it asks a provocative question. Are we looking at a dying star's last gasp or the birth cry of something entirely new? Neutron stars usually dance with partners of cosmic significance, massive stars, swirling gas clouds, or the crushing embrace of black holes. But in a quiet corner of the Milky Way, one stellar corpse has chosen an unconventional companion, a dwarf so small and faint it barely qualifies as a star at all. Designated Pulsar J0315 plus 0516, this system shouldn't work. The Neutron Stars companion is a puny failed star, a brown dwarf with less than 5% of our Sun's mass, barely capable of nuclear fusion. Yet somehow, this mismatched pair generates some of the most erratic signals ever detected from a neutron star, flickering between extremes like a radio with a dying battery. The first anomaly lies in their orbit. Most neutron star binaries circle each other at predictable, steady intervals. This pair wobbles like a drunkard, their orbital period varying by minutes with no discernible pattern. Every pulse from the neutron star arrives slightly early or late, as if some unseen force keeps nudging the system off balance, the leading suspect, the brown dwarf's chaotic atmosphere. Unlike true stars, brown dwarfs are turbulent worlds, their surfaces roiling with storms the size of continents. If this one's outer layers puff up unpredictably, engulfing the neutron star in tendrils of gas, the added drag could explain the orbital instability. But here's the catch. For gas to exert that much influence, the dwarf would need to leak material at rates far beyond anything observed in similar objects. Then there's the signal modulation itself. Normally, a neutron star's pulses are pristine, their clarity only slightly blurred by interstellar static. Pulsar J0315 plus 0516's emissions, by contrast, warp dramatically whenever the brown dwarf passes closest in its orbit. The pulses stretch and compress, their frequencies bending as if filtered through some celestial funhouse mirror. Some researchers argue this points to plasma tides, vast streams of ionized gas torn from the dwarf's surface and magnetically funneled around the neutron star. As these tides shift with the companion's rotation, they could act like lenses, refracting the pulsar's beam into strange new shapes. But the most tantalizing possibility involves magnetic synchronization. Brown dwarfs, despite their humble size, can harbor surprisingly potent magnetic fields. If this one's field interacts with the neutron stars in just the right way, it might trigger resonant effects, like two tuning forks vibrating in harmony, except instead of sound, they're generating bursts of distorted radio waves. Simulations suggest such a partnership could produce the observed signal weirdness, but only if the dwarf's magnetic axis tilts at an exact 60-degree angle to the neutron star's spin. The odds of that alignment occurring naturally, astronomically slim. Yet the signals persist, taunting theorists with their irregular precision. What makes this cosmic odd couple so compelling isn't just their defiance of expectations, it's what they reveal about the hidden diversity of binary systems. If a neutron star can find synergy with an object barely more substantial than a gas giant, what other improbable partnerships might be lurking in the cosmic dark? Every erratic pulse from Pulsar J0315 plus 0516 whispers the same unsettling truth. Sometimes the universe's most illuminating discoveries come from its most unlikely pairings. Quantum mechanics is supposed to rule the microscopic realm, governing electrons, atoms, and particles too small to see. But what if its fingerprints were etched across something massive? That's the haunting question raised by Pulsar J0745-3410, a neutron star whose bizarre pulses behave less like astrophysical emissions and more like a quantum experiment writ large. Dubbed the quantum quirk, this stellar anomaly emits radiation that flickers between distinct energy states as if it can't decide which path to take, like a subatomic particle existing in superposition. Except this particle weighs 500,000 Earth. The strangeness begins with the star's pulse profiles. Most pulsars emit radiation in smooth, predictable curves as their beams sweep past Earth. The quantum quirk's pulses, by contrast, arrive in discrete steps, sharp jumps between specific energy levels with almost nothing in between. It's the difference between a rolling hillside and a staircase, each step precisely 1.78 mega-electron volts apart. This quantization is eerily reminiscent of how electrons orbit atomic nuclei, occupying fixed energy shells rather than continuous ranges. Except here, the phenomenon isn't confined to a lab-scale atom. It's playing out across an object 12 kilometers wide, with gravitational forces strong enough to bend light into knots. One hypothesis points to the star's crust as a quantum amplifier. Neutron star surfaces are thought to harbor crystalline layers of iron nuclei squeezed into bizarre, elongated shapes by the crushing gravity. Under such extreme conditions, these nuclei might vibrate collectively, forming phonon waves that interact with escaping radiation. Normally, these interactions would smear out into a continuum. But if the crust's lattice structure is perfectly regular, a cosmic-scale quantum dot, it could impose discrete energy filters on outgoing photons, creating the observed staircase effect. The challenge, maintaining that perfection under a neutron star's turbulent magnetic fields, would be like keeping a house of cards standing in a hurricane. Then there's the space-time twist. General relativity tells us neutron stars warp their local vacuum so severely that virtual particles, fleeting quantum fluctuations, might become trapped in their gravity, briefly gaining reality before annihilating. The quantum quirk's emission gaps align suspiciously well with the predicted energy thresholds for these particle pairs. Could we be seeing photons interact with a foam of semi-real particles at the star's surface, their collisions imprinting quantum signatures onto macroscopic radiation? It's a stretch, but not impossible. The star's surface gravity is strong enough to freeze virtual particles in place long enough to leave traces. The most radical interpretation involves quantum gravity. Theorists have long sought to reconcile quantum mechanics with general relativity, and neutron stars are among the few places where both regimes collide violently. If spacetime itself becomes quantized near the star, breaking into indivisible pixels, at the Planck scale, the quantum quirk's emission steps might reflect discrete units of curved space vibrating at specific frequencies. Picture plucking a guitar string where the fretboard is woven from the fabric of reality itself. While speculative, this idea gains traction from the star's 1.78 MeV spacing, a value that pops up in certain quantum gravity models as a fundamental energy grain. Of course, skeptics argue for more mundane explanations. The steps could arise from beat frequencies between two closely spaced rotational modes of the star, or perhaps some unknown plasma instability in its magnetosphere. But the precision of the quantization resists these simpler interpretations. Whatever the truth, the quantum quirk forces us to confront an electrifying possibility: that the boundary between quantum weirdness and cosmic-scale physics isn't just porous, it might not exist at all. Every pulse from this star is a challenge thrown at our textbooks, daring us to rewrite the rules. If quantum effects can scale up to something as monstrously unquantum as a neutron star, what other impossible phenomena might be hiding in plain sight? The universe, it seems, enjoys blurring lines and leaving us to piece together the erased divisions. For decades, FRB 1931 plus 24 was the universe's most dependable lighthouse, a neutron star whose radio beams swept past Earth every 1.3 seconds with such precision that astronomers used it to calibrate telescopes. Then, in 2003, the impossible happened. Without warning, its signal vanished entirely. Not a gradual fade, not erratic flickering. One rotation it was there, the next silence. For 6 long years, every radio dish pointed at its coordinates heard nothing but interstellar static. Then, as mysteriously as it disappeared, the signal snapped back on in 2009, resuming its perfect rhythm as if someone had flipped a cosmic switch. This wasn't just a glitch, it was a fundamental challenge to our understanding of how neutron stars operate. Theories erupted to explain this cosmic power failure. The leading contender involves magnetic field collapse, a catastrophic rearrangement of the star's internal dynamo. Picture a neutron star's magnetic field as a tangled ball of rubber bands under unimaginable tension. Over millennia, these fields naturally decay, but if they reach a critical instability point, they might snap into a simpler configuration almost instantaneously. During this rearrangement, the field could temporarily become too weak to power the particle acceleration needed for radio emissions. It's the stellar equivalent of a circuit breaker tripping, except in this case, the repair takes years as the star's internal currents rebuild strength. The problem, while similar field collapses occur in magnetars, they usually trigger violent X-ray outbursts. FRB 1931 plus 24's disappearance was eerily quiet, with no secondary emissions detected across any wavelength. Then there's the cosmic vandal hypothesis, the possibility that something physically obscured our view. Neutron stars plow through interstellar dust clouds and plasma filaments, material that could theoretically block radio waves like fog dimming a lighthouse beam. But ordinary cosmic debris scatters radiation rather than absorbing it completely, stretching pulsars into smears of static rather than erasing them entirely. To explain FRB 1931 plus 24's total blackout, you'd need an obstruction of unprecedented density, perhaps a rogue molecular cloud core or the debris disk of a shattered planet. Yet no such object was detected along the pulsar's line of sight, and the abruptness of both the disappearance and reappearance suggests any obscuring material would have had to move in and out of alignment with impossible precision. The most tantalizing explanation lies in the star's rotational history. Careful analysis revealed that during its silent phase, FRB 1931 plus 24's spin slowed slightly more than expected, as if some unseen energy drain was at work. This led to the radical idea of mode switching, where a neutron star's magnetosphere occasionally flips between two stable configurations. In the on state, charged particles flow efficiently along open field lines, generating the radio beam. In the off state, the magnetosphere might reconfigure into closed loops, trapping particles like a magnetic bottle and starving the emission mechanism. Think of it as a cosmic generator switching from transmit to stand-by mode, except in this case, the toggle mechanism remains utterly mysterious. What makes this signal failure so disturbing is its implication. If one pulsar can shut off this dramatically, how many others have done so undetected? Surveys suggest up to 10% of predicted neutron stars are missing from our galactic sensors. Could they be in extended off states, their beacons temporarily dormant? And if mode switching is real, what triggers it? Some speculate it could be tied to subsurface quantum phase transitions or resonant vibrations in the star's crust. Others wonder if external factors like dark matter accumulation or gravitational waves from unseen companions might flip the switch. When FRB 1931+24's signal returned in 2009, it did so with unnerving perfection, picking up exactly where it left off as if its 6-year absence was merely a cosmic snooze. This effortless resumption hints at processes operating on timescales we barely comprehend, a reminder that even the most predictable objects in the universe reserve the right to break their own rules. Every silent second from this cosmic lighthouse wasn't just an absence of sound. It was the universe whispering a challenge to our assumptions, daring us to explain why the most reliable clock in the cosmos decided just once to stop ticking. Astronomers have catalogued thousands of neutron stars, each with its own predictable radio fingerprint, until they met VLA J0243+62, the cosmic rule-breaker. This stellar outlier emits a steady stream of radio waves at 48 GHz, a frequency so high it should be physically impossible for a neutron star's known emission mechanisms. It's the equivalent of finding a candle blazing with the intensity of a supernova, defying not just expectations, but the fundamental equations governing how these objects radiate energy. The impossibility lies in the physics of curvature radiation. Normally, neutron stars generate radio waves when charged particles spiral along magnetic field lines, releasing energy proportional to the field's strength. For VLA J0243+62 to reach 48 GHz through this process, its magnetic field would need to measure at least 10 to the 16th Gauss, orders of magnitude stronger than even magnetars, the most magnetic objects known. Yet observations show no accompanying X-ray signatures, the telltale markers of such extreme fields. It's as if the star is cheating, producing high-frequency waves without the required cosmic machinery. One faction of theorists argues we're witnessing a new class of emission, perhaps quantum phenomena scaling to macroscopic levels. Imagine the star's surface riddled with nano-sized antennas, regions where crustal vibrations couple with magnetic fields to amplify specific frequencies through resonant effects akin to surface plasmons in lab experiments. Another camp proposes relativistic beaming, jets of particles accelerated to near light speed by an unseen process, their radiation Doppler shifted to higher frequencies like a cosmic siren rising in pitch as it races toward us. But the wildest hypothesis involves vacuum breakdown. In strong enough electromagnetic fields, the quantum vacuum itself becomes unstable, spawning particle-antiparticle pairs that immediately annihilate. If VLA J0243+62's magnetosphere teeters near this threshold, the resulting cascade could generate broadband radiation with spikes at forbidden frequencies, effectively turning space-time foam into a natural particle accelerator. The challenge: this requires conditions so extreme they border on speculative, yet the star's signal persists with eerie stability, as if taunting our models. What makes this enigma critical isn't just the anomalous frequency, it's the absence of expected side effects. No hyper-strong magnetic field, no violent starquakes. Just clean, persistent radio waves where none should exist. Whether it's rewriting physics or merely exposing gaps in our knowledge, VLA J0243+62 stands as a stark reminder. The universe reserves the right to ignore our textbooks whenever it pleases. The Lorimer Burst didn't just surprise astronomers, it blindsided them. When Duncan Lorimer and his student David Narkevic sifted through archival data from the Parkes radio telescope in 2007, they weren't hunting for cosmic anomalies. They were studying pulsars, those predictable beacons of the universe, but buried in observations from 2001, they found something that defied categorization. A 5-millisecond flash of radio waves so powerful it couldn't have come from our galaxy. This wasn't just a new signal, it was a doorway into an entirely unexplored realm of astrophysics. What made this detection so revolutionary wasn't just its intensity. Though releasing a sun's monthly energy output in thousandths of a second is certainly staggering, but its solitary nature. Unlike later discoveries of repeating fast radio bursts, the Lorimer Burst stood alone. No precursor, no echo, no follow-up. It was as if the universe had shouted once into the void and then refused to repeat itself. This singular quality forced scientists to confront two unsettling possibilities. Either the burst was the product of an ultra-rare cataclysm, or our telescopes were missing countless similar events due to technological limitations. The Parkes telescope itself became an unlikely hero in this cosmic detective story. Originally designed to study hydrogen clouds in the Milky Way, its 64-meter dish and multi-beam receiver happened to be perfectly tuned to catch the burst's frequency range. Yet its very design also obscured critical clues. With a field of view spanning 4 full moons, Parkes couldn't pinpoint the burst's origin with precision. The signal's dispersion measure a telltale fingerprint of how much intergalactic plasma it had traversed, placed it billions of light years away, but the vast error margins left a shadow of doubt. Was this truly an extragalactic event, or could some bizarre terrestrial interference have mimicked the signature? Subsequent bursts only deepened the mystery. When astronomers finally detected repeating FRBs years later, they realized these phenomena fell into distinct categories, some erratic repeaters, others one-off explosions like the Lorimer Burst. The repeaters often traced back to magnetars or turbulent star-forming regions, but the lone wolves resisted easy classification. Their energy requirements beggared belief. How could any natural process convert stellar mass energy into radio waves with such efficiency? The leading theories, from collapsing magnetars to evaporating primordial black holes, all strained against the limits of known physics. Perhaps most frustrating is how the Lorimer Burst's uniqueness has endured. New telescopes like CHIME and ASCAP have since detected hundreds of FRBs, yet none match its precise combination of brevity, brightness, and spectral purity. Some researchers speculate it might represent an entirely distinct class of progenitor, a cosmic unicorn event where conditions align just right to produce something unrepeatable. Others wonder if we're seeing the aftermath of an exotic collision, like a neutron star plowing through a dense dark matter clump or a cosmic string snapping under gravitational strain. The burst's true legacy lies in how it reshaped our cosmic perspective. Before 2007, no one imagined the universe could produce such fleeting, powerful radio flashes. Now, FRBs rank among astronomy's most vibrant frontiers, with dedicated observatories scanning the skies for these ephemeral messages. Each new detection carries faint echoes of that first enigmatic signal, a reminder that the universe still holds cards it hasn't yet shown us. And somewhere in the archives of old observations or the static of future surveys, another Lorimer-like anomaly might be waiting to rewrite the rules all over again. Most cosmic fireworks come from grand galactic stages, spiral arms ablaze with star birth, or violent cores hosting supermassive black holes. But FRB 121102, the first repeating fast radio burst ever discovered, hails from a venue so humble it defies logic, a dim, unassuming dwarf galaxy 3 billion light-years away. This isn't just any dwarf galaxy. It's a fossil from the universe's youth, a pocket of primordial chaos where the rules of stellar physics seem to rewrite themselves. What makes this tiny galaxy, barely 1% the mass of the Milky Way, such an unlikely host for one of the cosmos' most energetic phenomena? The answer lies in its chemistry. Unlike mature galaxies brimming with heavy elements forged in generations of stars, this dwarf is metal-poor, its gas and dust still resembling the pristine conditions of the early universe. Low metallicity might sound like a technical footnote, but it's the key to understanding why neutron stars here behave so wildly. In such environments, massive stars live fast and die hard, their cores collapsing into neutron stars with properties that push the boundaries of known physics. Without heavy elements to carry away excess heat during their formation, these stellar remnants might retain more internal energy, resulting in hotter, more magnetically volatile cores. Then there's the dwarf's frenetic star-forming history. Hubble images reveal knots of intense stellar birth peppering the galaxy, suggesting periods of violent star formation followed by eerie quiet. This start-stop rhythm could create ideal conditions for neutron star oddities. When massive stars die in rapid succession, their neutron star remnants might cluster together, leading to close encounters or even mergers that trigger the bizarre bursts we observe. Some simulations suggest these dwarf galaxies act as neutron star factories, churning out exotic varieties like magnetars with ultra-tangled magnetic fields or hybrid objects straddling the line between neutron stars and quark stars that simply couldn't form in richer, more sedate galaxies. But the real puzzle is scale. How can a galaxy so small produce something so energetic? The answer might lie in its lack of competition. In a dwarf galaxy's sparse environment, there's little to disperse or absorb the burst's energy. Unlike in a crowded spiral galaxy where radio waves would battle interstellar plasma and magnetic fields, FRB 121102's signals tear through near-empty intergalactic space, arriving at Earth with unnerving clarity. It's the difference between shouting into a padded room versus an empty canyon one muffles, the other echoes. The most tantalizing clue comes from the galaxy's central region, where the FRB appears to originate. Deep spectroscopic analysis reveals an unusually high concentration of ionized gas, possibly the aftermath of a recent starburst or the glow of an active galactic nucleus. This turbulent environment could be the crucible where neutron stars are recycled, spun up, and magnetized by swirling plasma until they become the unstable powerhouses capable of launching FRBs. Imagine a cosmic demolition derby where stellar corpses are constantly bumped and jostled, their magnetic fields twisted like overwound springs until they snap, releasing bursts of energy powerful enough to cross the universe. What FRB 121102 and its humble host remind us is that size doesn't equate to significance. Sometimes, the most extraordinary cosmic events emerge from the quietest corners, places where the universe's primordial ingredients still linger, brewing up anomalies that challenge our understanding of physics itself. Every burst from this unassuming dwarf galaxy is a message from a simpler time when the rules were still being written and the cosmos was far stranger than we ever imagined. When a neutron star wakes from the dead, it doesn't just yawn and stretch its screams. XDJ1810-197, the so-called zombie star, spent over a decade in radio silence before suddenly resurrecting with violent, erratic pulsations that left astrophysicists grasping for explanations. The leading suspect, magnetic reconnection gone rogue. Picture a neutron star's magnetic field as a bundle of over-tensioned rubber bands storing energy with every twist. Eventually, something snaps, the field lines rupture and explosively realign, converting pent-up magnetic energy into a firestorm of radiation. This process routinely powers solar flares and magnetar outbursts, but the zombie star's prolonged dormancy followed by sustained activity suggests something far more extreme. Reconnection events typically last seconds, not years. Could this star have undergone a wholesale magnetic field collapse, its entire magnetosphere unraveling and rebooting like a cosmic computer crashing and restarting? Yet magnetic drama alone might not tell the full story. Crustal shifts offer another compelling angle. Neutron star surfaces are under unimaginable strain, crystalline crusts just a kilometer thick, balancing atop a superfluid core denser than an atomic nucleus. When these crusts fracture, the resulting starquakes can jolt the star's rotation and reignite dormant emission mechanisms. Imagine tectonic plates on Earth, but made of neutron-rich material harder than diamond, suddenly shearing under pressure. The zombie star's fits and starts pulsing could reflect these seismic aftershocks, with each new crack in its crust exposing hotter interior layers that briefly boost emissions before cooling. But there's a catch. Most observed starquakes cause single, sharp glitches, not the years-long erratic revival we're witnessing here. Then there's the cosmic wildcard, dark matter. Some theorists propose that certain neutron stars might accumulate weakly interacting massive particles in their cores over millennia. If these particles occasionally annihilate, they could inject sudden bursts of energy, destabilizing the star's internal equilibrium. For the zombie star, this might explain the abruptness of its resurrection, a dark matter time bomb ticking away in its heart until critical density triggers a chain reaction. The math is speculative but tantalizing. If just 1% of the star's mass converted from dark matter annihilation, it could power the observed activity for decades. What makes this signal so electrifying is how it blurs the line between known physics and cosmic speculation. Each pulse from the zombie star carries echoes of processes we've barely begun to map: magnetic catastrophes unfolding over stellar timescales, quantum fractures in kilometer-thick crusts, or perhaps whispers from the dark sector of the universe. Most neutron stars fade predictably into oblivion, but this one chose rebellion, clawing its way back from silence with a message we're still struggling to decode. Whether powered by magnetism, matter, or something even more exotic, its resurrection forces us to confront an uncomfortable truth. Stellar corpses might be far less dead than we ever imagined. The clockwork anomaly didn't just disrupt a single pulsar's rhythm, it sent shockwaves through one of astronomy's most ambitious projects, using neutron stars as galactic-scale gravitational wave detectors. For decades, pulsars have been the universe's most precise timekeepers, their rotations so stable they rival atomic clocks. Scientists relied on this predictability to build the Pulsar timing array, a network of millisecond pulsars acting as a spiderweb to catch the faintest ripples in spacetime. But when FRB 0933 plus 02 suddenly slowed down, it exposed a glaring vulnerability in this cosmic surveillance system. What if the clocks themselves are less reliable than we thought? Gravitational wave hunting with pulsars works like an interstellar game of telephone. As ripples from distant black hole mergers warp spacetime, they subtly alter the arrival times of pulsar signals across the galaxy. By comparing these tiny deviations, often just nanoseconds over years, researchers can reconstruct the wave's origins. The entire method hinges on pulsars being unwavering metronomes. But the clockwork anomaly proved they're not. Its unexplained deceleration was 100,000 times larger than the gravitational wave signals pulsar arrays are designed to detect, like a clock suddenly jumping backward while you're trying to time a hummingbird's wings. This leaves astronomers with a dilemma. Do they discard anomalies as rare glitches, trusting that statistical methods will average them out? Or does every unexplained timing shift hint at deeper physics we're missing? The anomaly's sharp recovery, snapping back to its original rhythm as if nothing happened, suggests these events might be invisible in archival data. How many past gravitational wave detections were actually neutron star hiccups in disguise? Some researchers are turning the problem on its head. If certain pulsars exhibit predictable anomalies, their unique fingerprints could be calibrated out, like noise-canceling headphones for cosmic static. Others propose hunting for anomalies deliberately, arguing these deviations might encode clues about neutron star interiors that steady pulsing never could. It's the astronomical equivalent of listening for skipped heartbeats sometimes. The breaks in rhythm reveal more than the beats themselves. The clockwork anomaly's greatest lesson might be humility. We've treated pulsars as perfect tools, but they're living, or at least evolving stellar remnants with complex inner lives. Their occasional rebellions don't just challenge gravitational wave astronomy, they remind us that the universe's most reliable phenomena still have secrets to share. Every glitch is a crack in our assumptions, and through those cracks, new physics might just come shining through. From the eerie whispers of XTJ 1810-197 to the gravitational riddles of GW 170817, these 25 unexplained signals aren't just cosmic oddities, they're cracks in the foundation of astrophysics itself. Each one defies expectations in ways we never imagined possible. Neutron stars that vanish and reappear like ghostly lighthouses, pulsars that arrive in mathematically perfect triplets, emissions that flicker between frequencies as if the universe itself can't make up its mind. These aren't mere gaps in our knowledge, they're glaring signs that neutron stars, the most studied stellar corpses in the cosmos, are far stranger than our models predicted. Take the quantum quark staircase like pulsars or the silent screamer's gamma-ray monologue signals so precise they mimic laboratory experiments on a stellar scale. Then there's the anti-glitch, where a pulsar suddenly braked instead of accelerated, or the Black Widow's distorted screams as it cannibalized its companion. Even the humble brown dwarf orbiting Pulsar J0315 plus 0516 proved capable of warping a neutron star's signal beyond recognition, revealing partnerships we never thought could exist. And let's not forget the wow signal's haunting possibility, that what we once called an alien broadcast might actually be the death rattle of a neutron star passing through an unseen phase of its life. What binds these mysteries together isn't just their defiance of physics, but what they reveal about the limits of human curiosity. For every signal we've catalogued, there's a glaring truth. Neutron stars are more than dense remnants of dead suns. They're laboratories for quantum gravity, engines of dark matter, even potential cosmic transmitters broadcasting on channels we've only begun to tune into. The Galactic Center Anomalies, erratic radio whispers, and VLA J0243 plus 62's forbidden frequencies suggest entire categories of stellar behavior we've yet to name, let alone understand. So where does this leave us in a universe that's equal parts awe and humility? These 25 signals are reminders that for every law we've written about how neutron stars should behave, the cosmos has scribbled a defiant footnote. Maybe some of these mysteries will yield to better telescopes or smarter algorithms. Others might require revolutions in physics we can't yet envision. But one thing's certain, the universe isn't just stranger than we imagine. It's stranger than we can imagine. That's where you come in. The next great discovery might not start in a lab or a lecture hall. It could begin with someone watching this video, staring at the night sky and asking, what if? So tell us in the comments, which of these signals keeps you up at night? Do you think the Lorimer Burst was a 1 in a trillion fluke, or a sign of something lurking in the cosmic dark? Could the zombie star's resurrection hint at entirely new states of matter? The conversation doesn't end here, it's just getting started, because in the end, science isn't about having all the answers. It's about having the courage to keep asking questions, no matter how impossible they seem. The universe is listening.